All right, let's dive right into this final installment of our MRI Physics Explainer. Today, we're uncovering the director's dials, the controls that create those stunning diagnostic images. And crucially, we're going to talk about the hidden dangers of the machine itself. We've spent our previous sessions geeking out over quantum spins and magnetic resonance, but today is all about the application. How do we actually take invisible physics and turn it into pictures that save lives? And equally important, how do we pull that off without putting a single person in harm's way? So here is our roadmap for today. We'll start with the master dials, move into crafting image contrast, explore fundamental pulse sequences, discuss the absolute need for speed, and finally wrap up with critical MRI safety and hazards. Section 1, the master dials. Let's put ourselves right at the MRI console. Imagine sitting in the technologist chair, staring at the two most critical controls you have for manipulating an image. These are the repetition time and the echo time. Think about the timeline of a scan. Your repetition time, or TR, is simply the gap between consecutive radiofrequency excitation pulses applied to the exact same slice of tissue. Basically, it's how long we wait before starting the whole process over again. Then you've got your echo time, or TE. This is the precise amount of time we wait between delivering that initial RF pulse and actually listening for the peak of the returning echo signal. Now, these two parameters are measured in milliseconds, but make no mistake, they dictate absolutely everything about the image we eventually see. Section 2, crafting image contrast. By just twisting these two timing dials, our TR and TE, the operator can completely flip which tissues light up on the screen and which ones fade out into the dark. We call this image contrast, and it relies entirely on the unique relaxation times of the different tissues in the body. Here's the cheat sheet for how these combinations work. If we go with a short TR and a short TE, we accentuate T1 weighting. That's looking at the recovery of longitudinal magnetization. On the flip side, if we use a long TR and a long TE, we get T2 weighting, highlighting the decay of transverse magnetization. And if we mix a long TR with a short TE, well, we essentially cancel out both of those effects. That yields a proton density image, where the brightness is just based on how many raw hydrogen protons happen to be hanging out in that tissue. Now, where this gets really cool is the real-world application. A fantastic rule of thumb for reading these scans is to check the cerebrospinal fluid, the CSF, in the brain or spine. CSF shows up dark on T1-weighted imaging, but it shines super brightly on T2. In fact, a classic radiologist trick to remember this is WW2. Water is white on T2. It's a lifesaver because it allows doctors to instantly spot fluid-filled abnormalities, edema, or inflammation just by dialing in those master controls. Moving on to Section 3, fundamental pulse sequences. Let's look at how the scanner actually choreographs the delivery of these magnetic pulses. A pulse sequence is essentially the computer code, the exact set of instructions telling the scanner when to fire radio waves and when to turn on the magnetic gradients. The absolute bedrock of clinical MRI is the spin echo sequence. Honestly, it's a stroke of pure engineering genius. It kicks off with a 90-degree RF pulse to tip the protons into the transverse plane. But because the magnetic field is never perfectly uniform, those protons quickly fall out of sync with each other. They dephase. To fix this, the scanner fires a 180-degree refocusing pulse at exactly half the echo time. This brings all those spinning protons right back into phase, creating a loud, clear signal called a Hahn echo. Think of this 180-degree refocusing pulse like a massive foot race. You fire a starting pistol, and the fast runners sprint ahead, while the slow runners trail behind. They are completely out of sync. But suddenly, you blow a whistle. That's your 180-degree pulse. And you tell everyone to instantly turn around and run back to the start line. Because the fast runners now have further to go, and the slow runners have a much shorter distance. They all cross that start line at the exact same millisecond. That perfectly synchronized moment, that's the powerful signal the scanner reads. On the other hand, we have the gradient echo sequence, or GRE. This sequence completely ditches that 180-degree turnaround pulse. Instead, it uses magnetic gradient reversals to refocus the spins. By skipping that extra 180-degree pulse, the scanner doesn't have to wait nearly as long, making the whole process incredibly fast. The catch? Because it doesn't actively correct for slight imperfections in the main magnetic field, it's highly susceptible to what we call T2 star effects. So comparing the two, it's a classic engineering trade-off. Spin echo gives us pristine, true T2 contrast that is amazing at reducing magnetic inhomogeneity, but it's relatively slow. Gradient echo trades a bit of that perfection for pure, unadulterated speed, allowing for variable flip angles and rapid data acquisition. Which brings us to Section 4, the need for speed. Because, let's be real, nobody wants to stay perfectly still inside a loud, cramped magnetic tube for an hour. If a patient breathes, shifts, or swallows, it can ruin the entire image. Engineers literally had to figure out how to accelerate this data collection. The solution is all about how we map the data. Instead of waiting through a long repetition time to collect just one single line of data for our image matrix, modern scanners can actually acquire multiple lines of data in a single TR. By rapidly manipulating the slice, phase, and frequency gradients, we can connect this abstract high-level physics directly to a high-resolution, lightning-fast medical outcome. This sparked a whole era of modern, fast imaging. We're talking techniques like fast spin echo, which uses an entire train of 180-degree pulses, and ultrafast Echo-Planar Imaging, or EPI. These have fundamentally changed the game, dropping standard brain scan times from 15 agonizing minutes to under 3. Meanwhile, sequences like steady-state free precession, or SSFP, use perfectly balanced gradients to maintain a steady state of magnetization. This gives us incredibly high signal-to-noise ratios and has completely revolutionized our ability to shoot real-time movies of the beating human heart. Finally, Section 5, MRI safety and hazards. And for our final act today, we really need a tonal shift. We have to step away from the life-saving beauty of these diagnostic images and look squarely at the potentially lethal power of the machine itself. We've got to ask ourselves, how does a machine designed entirely to heal become so incredibly dangerous if protocols aren't followed to the letter? You see, unlike an X-ray machine, which is completely inert until someone presses a button, an MRI's static magnetic field, the B0 field, is totally invisible, completely silent, and it is always on. To manage these intense, invisible risks, hospitals use a very strict 4-zone safety layout, recommended by the American College of Radiology. Zone 1 is open to the general public. Zone 2 is where patients are greeted but haven't been screened yet. Zone 3 is highly restricted. No one enters without passing a rigorous safety screening for metallic implants. And finally, Zone 4. This is the scanner room itself, the danger zone. The magnetic field here is at its absolute maximum, and tightly controlling who and what crosses this threshold is literally a matter of life and death. Without a doubt, the most terrifying hazard in Zone 4 is the projectile effect, because that powerful static magnetic field is always pulling any ferromagnetic object brought into the room. Think a pair of scissors, an oxygen tank, a wheelchair, or even a floor buffer can instantly be violently ripped into the center of the scanner. The machine essentially turns everyday metal objects into deadly, unguided missiles. But wait, the static magnet isn't the only hazard. Remember those radio frequency pulses we talked about for spin echo and gradient echo? Operators also have to obsessively monitor the specific absorption rate, or SAR. This is a safety metric tracking the rate at which RF energy is absorbed by the patient's body. Radio waves deposit energy, so too many pulses delivered too quickly can literally heat and burn a patient's tissues. The MRI system is constantly calculating this in the background to ensure the physics never cross the line into physical harm. It is an undeniably incredible machine, capable of peerless medical insight without using a single drop of ionizing radiation. But it demands total, unwavering respect and precise engineering. So I'll leave you with this. The next time you or a loved one are in that tube, listening to those loud, rhythmic knocking sounds, will you ever look at an MRI scanner the same way, now that you know the delicate, dangerous choreography of TR and TE happening right inside?